In the last session, we talked about general polarization state. And the electric field for the general polarization state will trace out a slanted ellipse on the xy plane. But the slant angle theta could be any arbitrary value. And the result is not going to be good for applications. So in this session, we're going to specify so-called the upright elliptical polarization state or the circular polarization state. And we're going to see what kind of condition we have to set for these two polarization states. Now we put some constraint on the phase difference between the two components. We first set this phase difference to be plus minus 90 degrees, and then put it into this general expression. But we still allow this EX0 and EY0 to be arbitrary. So with this phi equal to plus minus 90 degrees, if you are quick enough, you can see that this cosine becomes sine. So you can write down the conic equation to be just the upright elliptical equation. And in this equation, you can see that the axis length for this ellipse is equal to the amplitude of the x component of the electric field and the y component of the electric field. And also the slant angle is equal to 0. And remember that this slant angle is the angle between the major axis of the ellipse and the x-axis. Now with this theta equal to 0, you have an upright ellipse on the xy plane. Let's continue from the last page. We write down the two field components along x and y direction and allow the amplitude to be different. But we set the phase difference between these two components to be plus minus 90 degrees. And if you complain about this expression too complicated, then we can adopt the Jones vector expression. And so if you write down the Jones vector, the expression is going to be much easier because the phase difference here will give you plus minus j in this expression. But on this page, we're interested in knowing the angle between the net electric field with respect to the x-axis. And this angle is going to be equal to the arctangent of the y component electric field to the x component electric field. And let's look a little bit closely to these two expressions. If we have a plus minus 90 degree here, you can convert this cosine to minus plus sine expression. So when you take the ratio of these two expressions, then you will come up with tangent. But be careful about the sign in front of it. So if you use a plus minus sign here, you're going to have minus plus sign before this tangent. And before this tangent, you also have the ratio of EY0 to EX0, which is this one right here. And finally, you have to take the arctangent of the whole value to get this angle alpha. And now you can see that this angle alpha is a function of time and also z. So when we plot this ellipse on this xy plane, we already fixed the position of z. So if we allow this t to change over time, you're going to see that this alpha is going to increase or decrease over time. For example, if you choose this plus sign, this means that if we increase t, this alpha angle is going to increase over this direction. And so this means that if you try to detect the direction of the electric field versus time, it's going to do a rotation on this ellipse. And the rotation direction for this plus sign is going to be along the counterclockwise direction. And if you just point your thumb along the z direction, and then do a rotation of your 4 fingers, then you can follow the direction of the rotation of this alpha for this case. And therefore, sometimes we call this right-handed polarization. And similarly, you can follow this minus sign. And if you follow this minus sign, this means that you increase t, then the alpha value is going to be more negative. So it's going to go down this ellipse. And we call this the left-handed polarization, because now you can use your left hand to follow this direction when you point your thumb along this z direction. And z direction is coming out from this board. So a short conclusion is that this plus minus sign, minus plus sign, tells you the sense of the rotation of the electric field over time. And you have to be careful about the rotation direction when you want to tell people how the electric field will change over time. Now, I want to illustrate the concept of circular polarization by using this magic spring. And if I expand this magic spring, you can see a periodical structure along with it. And imagine that the electric field of the electromagnetic wave will trace out a circle during propagation. So the circle of this magic spring is going to match to the circle you draw on this whiteboard. And remember that this circle is the trajectory of the tip of the electric field of the wave. So think about that you draw the tip of the electric field over time, and you have a wave look like this. So you take a snapshot of the wave in space, and you'll be seeing this pattern. But this pattern is propagating at the speed of light in vacuum. So the whole thing is moving like this. And imagine that you put a plane in front of it, and this pattern will go through this plane. So on this plane, you're going to see the structured sample out trajectory similar to this circle on this whiteboard. And of course, if you have the magic spring in the reverse direction, then the direction is sampled out, the circle is going to be in the opposite direction. For example, think about you have a wave like this, and the period of this pattern is equal to the wavelength of the wave, and then it's propagating. So if you just look at along this direction and put the plane here, then you're going to see that the circular curve is going to rotate over time, because this structure will go in this direction over time. But if you reverse this magic spring in the opposite direction, then the sense of rotation of this circle is going to be reversed. So this is the concept of the circular polarization. Basically, the electric field will follow the circle and rotate on a plane you put into the space. And if you reverse the direction of this pattern, then the sense of rotation is also reversed. And I hope that you can catch the concept of circular polarization. And if you squeeze this magic spring in one direction, then the shape of this magic spring is going to be an ellipse. So you can also construct the concept of elliptical polarization by using this kind of structure. And again, there's a sense of rotation corresponding to how you wind this magic spring. And now let's try to set a more stringent condition to the amplitude. Previously, we allow the amplitude to be arbitrary, but now, in addition to setting the phase difference to be plus minus 90 degrees, we limit the two amplitude to be the same. So there's no major axis or minor axis for the ellipse. And with this condition, you'll end up having a circle on the xy plane governed by this expression. And this is the expression for a circle. So we call this the circular polarization state because the amplitude of the electric field is always the same because we set that Ex0 to be equal to Ey0. And now the tip of the electric field will trace out a circle on the xy plane. And again, this real expression can be simplified if we just describe it by using the Jones vector. And so for Jones vector, with this expression, you have a constant amplitude in front of the column vector, and then the x component is 1, and the y component is plus minus j. Then we know that this expression corresponds to a circular polarization state. And again, this plus minus sign will tell you the sense of rotation of the electric field. For example, let's try to calculate this alpha angle. And this alpha angle is the arctangent of this ratio, the y component of electric field to the x component of the electric field. And the result is going to be much simpler compared with the result from the elliptical polarization state, because you have the same amplitude in front of these two components. And once you convert this into sign expression, then you end up having a tangent of in the ratio. And when you take tangent of tangent, then you drop out the tangent expression from this equation. So the short conclusion is that this alpha angle now is a function of time and z, but when we plot the circle on the xy plane, basically we stand at one location of z. So now let's allow time to tick and to increase. So suppose that we pick this plus sign. So this means that this alpha angle will increase with time. So this means that this electric field is going to move on this circle along the counterclockwise direction. Conversely, if I take this minus sign, so when time increases, this alpha is going to be more negative. So this means that this tip of this electric field is going to rotate along the clockwise direction. And we call this the left-handed circular polarization. And for this case, we call this right-handed circular polarization. So again, the plus minus sign will tell you the sense of rotation of the electric field over time. In this session, we talk about elliptical polarization and circular polarizations. We first write down the general expression for the x component and y component of the electric field for a wave propagating along z direction. And we allow the phase difference between these two components to be plus minus 90 degrees. And we found that the electric field on the xy plane will trace out an upright ellipse. And the plus sign and minus sign before this 90 degree will tell you the direction of the rotation of the electric field. And if we further specify the amplitude of the x component and y component of the electric field to be the same, then we end up having an expression describing a circular polarization state. And again, the sign in front of the plus minus 90 degree will tell you how the electric field will rotate on this xy plane. So this is a few key points I want to tell you for this section. Thank you.